So it is a pleasure to be here, and indeed I'm going to give two lectures if you can stand it. The first one will be, as it were, the theory of tight binding, and then later on Thursday I'll talk about exactly what we've been doing with it most recently. And I think I said in the abstract that this whole tight binding thing does tend to go up and down in fashion, and I know in the late 70s it was a very big thing, and then along came the density functional theory and sort of blew it away for a while, and then it came back into fashion, and it comes in and out of fashion. And I know Jim Chaddy once told me he was a big chap in the semiconductor business and worked all his life at Xerox, and in the end he did all his calculations with tight binding, and when he knew the answer he'd then have to repeat them with density functional theory so that he could get it into physical review letters. So and then there's this rather nice slide I found in the, it doesn't show very well, but this is a scan from the second edition of P.W. Anderson's book. And he seemed to have been quite a self-important kind of person, doesn't he? I never met him, but he says, "I note that I guessed absolutely wrong in dismissing tight binding theory out of hand. In my present opinion, it's the right way to think about most bonding in solids." So it is a way to think about how the atoms in a solid are bound together. So it's an approximate way of thinking and calculating about the properties, the electron and structural properties in condensed matter, both liquids and solids. So in today's talk, the outline is like this. I will, as quickly as I can, try to take you through the traditional, what you might call the old non-self-consistent, goes back to Walter Harrison's famous work, and I'm going to take it that you're all great experts in the density functional theory, which you all are, I suppose, and that you have some background in solid-state physics, otherwise it'll be relatively pedagogical. And then this is the thing that I invented with Mike Finnis. There's a polarisable-ion self-consistent tight binding theory. I'll try to take you in detail through how that works. A few years later we discovered magnetic tight binding, and that means we can now deal with polarisable, mixed covalent, ionic solids. We can deal with magnetic solids and liquid, or magnetic solids, polarisable liquids. So then I'll talk to you about polarisability, and then if there's time at the end I'll say a little bit about time-dependent tight binding. So the traditional non-self-consistent tight binding approximation, it goes back to Walt Harrison and his observation that the energy bands, these are the dispersion relations for electrons in solids, the eigenvalue of the electron plotted against its wave vector in the usual way, and he noticed that the best calculation that they could do at the time, maybe I'll use the pointer, which was in the old empirical pseudopotential method, looked very, very similar not only to the free electron bands, apart of course from the missing band gaps, but to a simple tight binding calculation. So his ansatz was that one can very easily make tight binding bands based on perturbing free electron bands, just like one can make pseudopotential bands based on the perturbation of a free electron gas. So that immediately allowed him to start guessing what sort of parameters would be needed to build a tight binding model for the semiconductors. So to start at the beginning, if one's interested in a particular piece of matter, then it has atoms, and you have to decide for yourself which orbitals you think are important for the atoms in question. There'll be s, d, p orbitals, and then you take them out of your bag and you put them onto the atoms in question, and you try to solve the Schrödinger equation for a wave function which is compounded of these orbitals. So let's just start with s orbitals. In our simple case, we have s orbitals on a bunch of atomic sites. So the notation is always a capital R, which is a vector for the position of an atom. If we just put an orbital on every site then and add them all together, that doesn't make us a Bloch function. It doesn't make a wave function that satisfies Bloch's theorem. So we multiply each one by a phase factor and we construct what's called a Bloch sum. And that works because then if I ask what's the wave function displaced by some lattice vector, I get the wave function that I had previously times a phase factor, which is Bloch's theorem. So the task is to take the orbitals out of my bag, put them onto the atoms, multiply them by suitable phase factors, and I have a wave function, and then for that I need to find the wave function that solves the Schrödinger equation so that I can find its eigenvalues. So again, I now have a dispersion relation, the eigenvalue as a function of wave vector. I need to calculate integrals of these type for a Hamiltonian H0 because we're talking at the moment non-self-consistent type binding, so we'll put a superscript 0 on it for that. So we make an ansatz that the Hamiltonian contains a potential which is the sum of potentials centered on atomic sites. And then we can expand out the two integrals that we need. They look pretty horrible because there are terms coming from three different sites, possibly an R primed, and an R double primed. So there are Hamiltonian matrix elements, so-called, and overlap integrals. Now, at this point, when you draw a line here, you may be doing something like siesta or something. You may be doing an ab initio calculation if you actually knew what the orbitals were, and you could be bothered to carry out all of these integrations. But we don't want to do that in tight binding. We're trying to build a toy, a model. So first of all, without hardly any justification at all, we neglect all the difficult three-center integrals. Those are ones for which every term comes from a different site. And we also neglect overlap integrals, except for the case in which the two orbitals are on the same site. So this is traditional self-consistent tight binding. What we're left with, we still don't even calculate those. We try to find a lookup table for those by fitting or other kinds of procedures. So what we're left with now are only two-center terms involving orbitals on two different sites. So there are two cases. Here's the case where there are two orbitals on different sites and the potential comes from one of them. So a two-center term like this is the most important terms, the hopping integrals, so-called transfer integrals in many body language. We give them a symbol H or a symbol T is what the Hubbard people use. And these are the things that we need to find, because then we can develop the band structure on a simple formula like this. We can do that because the on-site term, the term which involves only quantities on one site, a potential and two orbitals all on the same site, we may as well put the kinetic energy in there too. And here we have essentially an atomic term value, which again we can look up in tables if we like. These green things are a little problematic. This is the case when both orbitals are on the same site, but the potential's coming in from an atom on a different site. And some of you will be familiar with that sort of thing in what they call ligand field theory in quantum chemistry. You might have a cage of oxygen ions with the transition metal ion in the center, and its orbital levels are split by the field and field gradients, the electric fields from those oxygen ions. It's not spherically symmetric, and so the different d orbitals typically are split by raised or lowered by different amounts. Now, for the moment, we neglect these crystal field terms. I'll show you how we put those back in again in our self-consistent scheme. And so we have hopping integrals, transfer integrals, which in this case make up a sigma bond out of s orbitals. So far we've been thinking only about s orbitals, but we may be thinking about other orbitals. We might need a whole zoo of these different kinds of bond integrals connecting orbitals of different angular momentum. The s orbitals, there's an sp sigma, a pp pi, and a pp sigma, and so on. So we might need to have parameterized or taken from somewhere values of all these different hopping integrals for the orbitals that we've put into our solid. Going back to simple cubic S-band, going back to s orbitals and put them onto a simple cubic lattice, you can develop the whole thing analytically, and you can draw the band structure. This is now the dispersion relation, the band structure along high symmetry lines in the Brillouin zone. What I've drawn in the dotted line is the free electron approximation. You can see near gamma, tight binding and free electron theory always merge together, because when you expand a cosine, you get a square. A quadratic, and here's the density of states, very different in the tight binding, at least as soon as you get away from the bottom of the band. And again, if we had p orbitals rather than s orbitals, then the thing gets a little bit more complicated. The Bloch sum has an additional sum over orbital types. Of course, one could also at this stage add s and d orbitals. In the case of just a p-only model, in the case of p-bands, one has a 3x3 secular matrix, and one has to solve the Schrödinger equation in that way. So it does become a little bit more complicated. And then again, if it's not simple cubic, but there are bond angles, then one has to consider that the quantization axis of the p orbitals, for example, may not lie coincident with a particular bond direction, or it might not be perpendicular. And so in a case like this, when one lays off an angle theta between the bond itself and the quantization axis, then the bond integral then becomes a linear combination of sigma and pi bonds in that way. And so to generalize that, as Slater and Costa did in 1954, one thinks of the three direction cosines of a bond, and one can also always calculate two center integrals in terms of the fundamental bond integrals that I showed you. and the direction cosines of the bond. And Slater and Costa tabulated all that in the famous Slater-Costa table. It's complicated, but you can program this nowadays into a computer. When you know the direction cosines of the bond and you know what the various fundamental bond integrals are, then you can calculate any Hamiltonian matrix element that you need. Here's the SPD block and here's the DD block. And once in your life you have to differentiate this so that you can do the forces, but you do it once and then you have it in your computer program, and if you're lucky someone gives it to you. But it was a bit of a mess. We had to do that when I was a student. So the simple cubic p-band is actually quite easy to do because the secular matrix is already diagonal, because all the bonds are along the x, y, z directions, and so one can solve that. One has a pp pi integral. There are pi bonds and sigma bonds, and if we take it that the pp pi is small compared to pp sigma, we have a nice simple band structure which I've plotted here, and a density of states which I'm showing you. So it's always useful to plot the energy bands and then to plot the density of states next to it on an upright plot like that. And so it's all very straightforward, and you can see here I've plotted again along the high symmetry directions. And that's it looks pretty simple. Here's strontium oxide, here are density functional theory energy bands, here are tight binding bands. You can see the signature here of the simple cubic p band is exactly as I showed you a moment ago in the ligand orbitals in the so-called valence band of the strontium oxide. So it's not a bad way to calculate band structures, and of course you can make it more and more complicated. So self-consistent tight binding, people have thought that we weren't the first people to think about it, but since we have solved a Schrödinger equation, we have eigenvectors, and if we look at the eigenvectors, we'll see what the charges are on the atoms after a single solution of the Schrödinger equation. Some charge will move from one atom to another. We get some ionicity. Well, normally in ordinary old-fashioned tight binding, you just ignore that. You do a single solution of the Schrödinger equation, calculate your forces and energies, and you're done. But if you imagine that we're interested in those charge transfers, and we ask then, they will of course perturb the Hamiltonian matrix. So if charge sloshes onto a particular atom, that will raise its on-site energy level by some amount, proportional roughly to some kind of Hubbard U, some energy. Then one will want to feed that back into the Hamiltonian and cycle through till one has a self-consistent solution. And really all we have is charges as point objects. It's not like density functional theory where you have the charge everywhere in space. Each orbital just exists, if you like, as a kind of a point object associated with every nucleus. So one can accumulate point charges and calculate a Madelung energy and a Madelung potential. We wanted to go a bit further than that because we believed that in lots of interesting situations, for example, particularly transition metal oxides that we're interested in, there will be not only point charges accumulating, but point dipoles and point quadrupoles. So we tried to generalize the thing a little bit to produce a polarisable-ion self-consistent tight binding theory. And it works a little bit like this. So let's suppose we have an atom at the origin and we have an atom at some other lattice site, capital R, and charge is accumulated around this site R, but it's localized. So there's a charge density and the vector R primed is a little vector in the neighborhood of the atom R. So some charge has accumulated here, and we can expand that in point multipole moments. So we say that it's totally localized here, then this charge is all localized on its atomic site, and we can think of it as a point charge plus a dipole plus a quadrupole, etc. So we can imagine that we've developed a multipole expansion of the charge on the site R. And now we look at the site in this case we put the site at the origin for simplicity, and we say, well, what does that look like? What does the charge distribution there look like when I'm sitting over here? So what potential do I see? What electric potential do I see due to the multipole moments of the charge over here? So now I focus on a little vector R which is in the neighborhood of the origin, and there's an electric potential V naught of R, 0 being the label of the atom 0, due to the charge distribution over here. And I can expand that into spherical waves, and then I can ask what are these expansion coefficients. So I'm using a notation of capital L, which is a compound notation of the L and M angular momentum indices, and again capital R is a site index. So written again now more generally, there's a site R and I'm asking what is the electric potential at site R due to multipole moments at other sites around, and I expand that now. So I should just explain. Here I used an index 0 because I'd put the atom in question at the origin. Now let's put it at a general site R, and now solve the Poisson equation. So this is just standard electrostatics. We took this out of Jackson. So all of the multipole moments on the sites are primed, and all the sites are primed. All the L pole components of the charge are expanded out. And the solution to Poisson's equation is this, that the coefficients of the spherical wave expansion of the electric potential at site R is given by all of the multipole moments on all the other sites R multiplied by coefficients. Of course, this would be, in the point charge case, it would be very simple. This would just be 1 over r minus r primed. It would be the Modell potential. But it's a bit more complicated when you're dealing with multipole moments. Turns out that this matrix here is actually nothing other than the famous KKR structure constants from electronic structure theory. So we had these all along. I was talking to Michaela just yesterday about when we were first thinking about this. When Mike Finnis first wrote down the theory, he wrote everything down in terms of Wigner coefficients, Wigner symbols, and I found the maths too hard. So I had another go at it, and I discovered that we could also do it in this way using these spherical tensors. So what you have here is a Hankel function, this thing here, and these famous so-called Gaunt coefficients, which are multiples of standard spherical harmonics. So just to go a bit more simply, to repeat what I just said, the electric potential is expanded in spherical waves. Its coefficients are related, they're proportional to the multipole moments of the charge, which give rise to the electric fields and field gradients. And so B is a kind of Modell matrix, and they feed back into the Hamiltonian. So now we have our self-consistent, our non-self-consistent, old traditional Hamiltonian, plus an additional part which accounts for the self-consistency. And in our theory, this is not a small term, this is not a perturbation theory we're going to do. We're just going to say we divide the Hamiltonian into these pieces. And the H primed now is sites diagonal. So we only have terms in which R and R are the same. So we have on-site terms, but we have terms that link the different orbitals, the different L angular momenta on a particular site. So there's a Hubbard U, so as charge accumulates on the site, that raises the Hamiltonian matrix elements on that site, on the site, and tends to reject the charge again. So this resists charge accumulation. And here are the crystal field terms. So now we have the thing that was missing originally, and we have these new, what you might call crystal field parameters, which are new parameters of the model, which show how the L primed, L double primed orbitals are split by the electric crystal field. And here are the Gaunt coefficients coming in a second time, acting as selection rules. And so there's only a small number of these coefficients that have to be found, and again they become parameters of the type binding model. So non-self-consistent type binding in the good old-fashioned way, there was a band energy. I've shown you how to develop the electron dispersion relation to get the one electron eigenvalues. You sum up the occupied eigenvalues and you have something called a band energy, and then you add an additional term which is a pair potential, a pair energy, which is normally a repulsive term, and those two contribute to give us a type binding model. Now in our self-consistent type binding, we put a 2 here for reasons I think should become apparent in a moment. So we have if you go back to the previous slide, we have the, if you might call the first order, as you might think of it, non-self-consistent type binding total energy. Now we have a second order, we have a band structure energy, a pair potential energy, and we have a thing we call E2, a sort of second order energy. Now, again, the band energy is just the trace of the density matrix with the Hamiltonian. I am already anticipating magnetic type binding here by making a sum over the spins, sigma being plus or minus 1 for the up and down spin channels in the magnetic system. And our second order energy comes from the two terms I showed you before in the self-consistent Hamiltonian, the Hubbard U term, which is a U times a charge squared. There's additional terms here I'm going to explain in a moment coming from the magnetism, and then the Modell part, the Modell energy, the bit that gives rise to the crystal field terms and the polarization, is simply a sum of multipole moments times expansion coefficients of the electric potential. So this is now a second order energy. If I differentiate this with respect to the charge, I'll get the Hamiltonian, which I showed you a few slides ago. And we have a force theorem, so we can do molecular dynamics. So the force is, I need the gradient of the non-self-consistent Hamiltonian, so that's just like old-fashioned tight binding. I take my Slater-Coster table and find all the derivatives, and then I take the trace with the self-consistent spin density matrix. That gives me the derivative of the band energy. Pair potential is trivial to differentiate, and there's an additional term comes looking a bit like the Hellman-Feynman force. So there's a force that comes from the gradient of the electric potential. Now, for those of you who like density functional theory, and it goes all the way back to Matthew Falks when he was doing his PhD thesis with Roger Haydock, he wanted to ask the question, why does tight binding really work? What's it got to do with density functional theory? And lots of work has gone into this. Farnheim did a lot of work, Mike Finnis did a lot of work, and it turns out to look a little bit like this. If I take a Holmberg cone total energy functional and I expand it about some trial input density, and I have a delta R, which is the difference between the self-consistent spin density and the trial density, then I can write this expansion exactly. And this is the exact total energy, except for errors in the exchange correlation part. Now, this was first done by Matthew Falks, and this is now called the Harris-Falks functional by almost everybody. It was done independently by John Harris and Matthew Falks. This is what we were doing many years ago when you were all still too young to bother, when computers were very, very expensive and very slow, and it was hard to make density functional theory self-consistent. So a lot of us were just calculating the Harris-Falks energy. We were guessing a trial density and appealing to the variational principle that these second-order terms were sufficiently small. So that, if you like, is an analog. And then Finnis, Pettifer, Sutton, they proved that with a certain ansatz for spherical atomic densities, one can show that this term here is almost a pair potential in density functional theory. So their supposition was that tight binding works because this is the band energy, as I've shown you a moment ago, in the non-self-consistent Hamiltonian, and these are all pair terms. They worked all these out for spherical overlapping charges and found they're almost all pairwise except for the exchange correlation part. Certainly the Hartree part is pairwise, and that was almost pair potential wise. However, if we want to go further, we can identify these second two terms with parts of our tight binding theory. So, for example, this term here accounts for the electrostatics I was showing you. So in tight binding world, we can make a self-consistent band structure calculation now, applying that second order term, and you can see, for example, that the crystal field effects reappear quite automatically. So here I'm showing you band structures for fluorite and hypothetical rutile structure in zirconium dioxide, and comparing density functional theory with tight binding. The only point I want you to notice is that the crystal field splitting of the D manifold is taken care of automatically through those delta parameters that I showed you. And we used this in calculating some properties of zirconia. That's why we developed this theory in the first place, because we were interested in this phase transition from the cubic to the tetragonal phase. We wanted to see whether this was a first or a second order transition, and we wanted to calculate the free energy. And we were able to do that using this tight binding model. So the magnetic tight binding, on the other hand, is a way of addressing this final term, the on-site term. So if you like, these are the intersite parts of the Hamiltonian, and these are the on-site parts of the Hamiltonian. And we want to ask whether we can mimic this density functional expression within a tight binding model. So we write it in this way. We write it as we write that second derivative of an exchange correlation kernel as a first derivative of an exchange correlation potential in a spin channel sigma. And we say, what can we do about making a tight binding model? So we will have an input density, which will be our rho in, if you like, the density that generates the non-self-consistent Hamiltonian. And we'll construct it in a way that the up and the down channels both have the same amount of charge. So we start with a trial density which is non-spin polarized. So each has half of the total charge, and we define a delta rho sigma as the difference between the self-consistent and the input spin densities, like that. And we at the moment is then the distance. Now the moment is the same as the delta moment because the input moment is 0. So as the system is made self-consistent, that procedure introduces a spin moment m, which is an imbalance between the up and down spin channels. And so we can proceed and examine these functional derivatives and associate the functional derivative of an up channel with respect to a down channel charge, or a down channel charge with respect to an up channel charge as our Hubbard U, and we can identify the like spin derivatives as a U take away some other positive number. The notion is that, in terms of the physics of it, that this is all on site. So two electrons who, if you have an electron already on the site and another electron comes along of the opposite spin, then there's a Coulomb interaction which repels it. And that's this U here. But if an electron comes along with the same spin, so either they're both plus or both minus, then the repulsion is slightly smaller because the Pauli principle anyway sees to it that they tend to stay away from each other. And so the Hubbard U is diminished slightly by a quantity I, which is conventionally called the Stoner parameter. And then when we carry out the integrals, the derivatives rather, we find that the derivative of the exchange correlation kernel with respect to the charge, a second derivative, is U take away a half I, and we see an identification of the Stoner parameter as a second derivative of the exchange correlation with respect to the moment, the magnetic moment. And so finally, putting all that back together, we have an expression for our tight binding second order energy, our Hubbard energy, which looks like this. So there's a U take away I times the square of the charge, and this is a very, very famous term. I'm sure you've seen that before in your solid state physics. It's the Stoner energy. So it's always a quarter Stoner parameter times the magnetic moment squared. And this is nicely consistent with LDA plus U, if you like that sort of thing. So if you go back and look at the papers by Anisimov, Anderson, Zahn, you will see that in the LDA plus U, one writes the on-site energy like this. And these authors rather cleverly just did some algebra and proved that that line is equal to that line, which is actually very revealing because it shows the first two terms are dependent only on the total charge, and the final term depends on the charge in the separate orbitals. So what you have here, when you differentiate this energy, you'll have three potential terms, and it's only the third term which will be orbital dependent. And that takes you well away from local spin density approximation. The local spin density approximation doesn't know about orbitals, it only knows about density. So in the spirit of the LSDA, we could neglect this term and consider only these two terms. If we put this term back in again, we'd have something like a tight binding plus U, which would be more powerful than LDA plus U, only in the sense that these U's and J's are averaged. In the old Sascha-Lichtenstein version of the LDA plus U, these U's and these J's came inside the summation signs and they carried M-primed indices, and so then for each different orbital would be a different U and J. If you average or spherodize them, you pull them outside, then the only term left that's orbital dependent is this one. And if one includes terms like that, one can put in things like the self-interaction correction. One could do that back into tight binding. But for simplicity, for the moment, we retain only these two terms. And doing so, we can do some further manipulations, and we arrive at our energy E2, which I derived a few moments ago. So what we've done is consistent with the LDA plus U. That's the only reason I wanted to do it. And the J, of course, from the LDA plus U is nothing other than the Stoner parameter. And you can see what's going on here. If I ask what's the potential in the sigma spin channel, I differentiate the on-site energy with respect to its density, and I get just these two terms, and then I say what's the difference between the potential for spin up and spin down, and it just turns out to be exactly what you'd expect, the Stoner parameter times the magnetic moment. So it's all completely consistent and quite elegant. Incidentally, one could do something else that we discovered, which is one could go back to the Harris-Falks functional, and instead of having a trial spin density which was 0, we'd start with a trial density which has a magnetic moment on it, M in. And then we ask, what's the first order total energy? So the first order total energy in the Harris-Falks approximation looks like this. And when we compare that m in to the, so if we compare E m in to E0, we get what's called the magnetic energy, and it looks exactly like a Stoner model. So the Stoner model is actually consistent and identical to a Harris-Falks functional in which the spin density is variational. You can imagine that you construct a bunch of trial densities which all have the same electron density somehow, but have different spin densities, and then you ask which of those family of densities minimizes the Harris-Falks functional, and you come up with a Stoner model. What it means, of course, is because this is non-self-consistent, because this is a first order trial density, the point is that even though here's a calculation of the density of states of BCC iron, ferromagnetic iron, both in the tight binding model and in the local spin density approximation. The point is that one doesn't, in the Stoner theory, in the first order theory, need to know what the spin polarized density of states is. It's adequate to know only what the non-spin polarized density of states is. This was a point made by Ole Anderson a very long time ago. Here is the non-spin polarized density of states of iron with its Fermi level right there in the middle of that peak. And you ask the question, well, suppose I wanted to start spin polarizing that density. What would I have to do? I'd have to take charge from just below the Fermi level and flip its spin. If I flip its spin, then of course the Pauli principle says it can't stay there anymore, because there are now two states of the same spin and the same energy. So not only do I flip its spin, which might gain me some exchange energy, I've also got to flip it to above the Fermi level. And so I do that. I take a bit of charge like that and I pop it above the Fermi level. So that gains me exchange energy, but I pay a price in kinetic energy. So now suppose I want to spin polarized a little bit more. Now all the states around here are spin polarized, so I've got to take charge from slightly further down below the Fermi level, and I've got to increase its energy by a little bit more to get it into the unoccupied states above the Fermi level, and then I've got to do that again. And so as you can see, generally speaking, if I want to flip a certain number of spins, I've got to go through this process. I've got to take a little bit of charge, let's say a half dm primed, and I've got to split it. And so what's important is the average density of states, or the area in this rectangle. And so the process which I've just illustrated is an essential integration right up to the moment that I want to produce. I've got to take little bits of dm primed and I've got to flip them, and the amount of kinetic energy that it costs is inversely proportional to the height of the density of states. And so this average density of states come under there in the denominator. So that's the kinetic energy lost, and I gain some exchange energy. So this is my magnetic energy. And you can show that this is stationary at this very well-known generalized Stoner condition, that the average density of states associated with the particular moment that you're interested in multiplied by the Stoner parameter has to be 1. So Ole Anderson invented this construction, which is very neat. For every density of states, you can calculate a curve like this, which says what is the average density of states given that I've flipped m or half m spins. So to generate a moment m, this is the average density of states, and so the stationary condition is a graphical construction. I simply have to find the intersection of 1 over the Stoner parameter, which is just an energy. I just draw it as a straight line, so I just have to find the intersection of that with this curve, and I get the equilibrium magnetic moment. So I've done that here. I've just taken the tight binding density of states and put it through this construction, and you see this nice Ginzburg-Landau kind of thing. And this is just an illustration of the Harris-Falks approximation. Here I've just taken a trial density with the same charge density but different magnetic moment, so I've varied the magnetic moment, and I've calculated the different contributions to the energy. And it turns out that the exchange correlation energy, this dotted line, is strictly quadratic. This is iron, but it should hold for most transition metals, which means that it doesn't actually matter what you use for your trial moment, because the Stoner term is always a half m squared, half im squared, and as long as the exchange energy is quadratic, then the Stoner parameter is a constant and doesn't depend on the magnetic moment. The quadratic part, the non-quadratic part, actually comes from the valence kinetic energy, which has quadratic and quartic terms in it. And that's what gives you eventually a minimum. Otherwise you wouldn't get a minimum in this. So it's like a Ginzburg-Landau type of formula. You have a quadratic part and a quartic part, and the quadratic part comes from the exchange correlation energy. So that's the magnetic type binding. We're going to come in the lecture on Thursday to some applications and work that we're doing on iron and steel. Let me talk a bit about polarisability now. So we have this polarisable ion type binding model, so that in the self-consistent procedure, if we're dealing with an ionic, mixed ionic covalent system like a transition metal oxide, then the self-consistency will generate multipole moments on the ions. And this was very important for us when we tried to we did publish work on zirconia, because we could see that the zirconia is an interesting substance with many different phases as functions of temperature. So it has a monoclinic phase, a cubic and a tetragonal phase. And we found that to predict the monoclinic phase required us to use a type binding model including quadrupole moments developed on the oxygen ions, and it's the behavior of these moments that also control the off-centering in the transition from cubic to tetragonal in the zirconia, and this has many implications in what's called the stabilization of zirconia, the cubic stabilization with calcium and yttrium, and it has also implications on the well-known transformation toughening of zirconia ceramics. But here I want to talk a bit about molecules. We were told by Ali Alavi to have a look at azulene, which is a funny molecule. It's like naphthalene, same number of atoms, but naphthalene is two 6-membered rings stuck together. This is a 7-membered ring stuck to a 5-membered ring. And that has a permanent electric dipole moment in the ground state. Here it is. So in the ground state, there's a dipole moment pointing from left to right, from the 5-fold to the 6-fold ring. Now what I can do is I can put this molecule into an electric field and I can relax it, and then with the type binding program I can measure the dipole moment. And that's what this straight line is here. The dipole moment is a function of the electric field. I could do the same in density functional theory, which I did, and that's the dotted line. Now I did some fitting. I fitted this point here, but nothing else. So the type binding was remarkably faithful. Now what's the other interesting thing about the azulene molecule is if you go to the first excited state, so you take an electron out of the what's called the HOMO, the bottom of the valence band, and put it into the conduction band. That's a very, very crude and childish way to do an excited state, but I can do that, and if I close my eyes I can make that self-consistent under the constraint that I have a hole at the top of the valence band. And then I have an excited state, and in fact what happens in azulene is well known, is that the dipole moment reverses its sign. It goes then from right to left. So this is now what I did, and again in the density functional is the dotted line, and the solid line is the type binding, and the slope of that line is the polarisability of the molecule in the ground state and in the first excited state. And we could do that, and we can compare to density functional theory, and we can compare to experiment. Incidentally, we did the same. I won't say any more about paranitroaniline. It's a much more complicated system, but we can do similar things there as well. So that's interesting enough, really. If you take an electron out of the so-called HOMO, you know what that is, that's the highest occupied molecular orbital, and put it into the LUMO, the lowest unoccupied molecular orbital, you get the structure that I was calculating here. But those two are uncoupled. There's no dipole moment connecting those two wave functions. This is something called the violation of Cash's rule in molecular optics. There is only coupling to the second excited state when you take an electron out of the HOMO and put it into what they call LUMO plus 1. So I want to come back to that in a moment. So finally I want to tell you a little bit about the time-dependent type binding. It's not at all trivial. There's a number of very, very deep and thoughtful papers by my colleague Tchavdar Todorov who invented this. These, incidentally, are I've just plotted the eigenvectors of the three states of the molecule, the ground states. So cyan and magenta show whether the eigenvector is positive or negative on that site, and the intensity of the color shows you the amount of charge or the amount of weight of the eigenfunctions on each of these atoms. And interestingly enough, in the ground state, the HOMO plus LUMO plus 1 and LUMO plus 2 state, all of the weight resides in the pi system. So you've got a lovely molecule in which in these particular states, these particular eigenstates, there is only weight in the pi system. So we're only looking at pi electrons here. So everything becomes very clean, and you can, by simply calculating the dipole matrix elements between the different states, you can see that 1 and 2, 0 and 1 and 1 and 2 are uncoupled don't see each other in the dipole approximation, but there is coupling between the ground state and the LUMO +2 state. What we then did, we got our student to write a code, and the time-dependent type binding essentially generates a dynamic. Well, it does many things, but one thing it can do is generate a very simple dynamics like this. So it's like a quantum Liouville equation with some damping. So because, generally speaking, the density matrix and the Hamiltonian commute, nothing will happen here unless you drag it from its excited state, for example, with the density matrix rho into the ground state rho 0. And in order to preserve the idempotency of the density matrix, one has to set the gamma to 0 for any diagonal term in rho minus rho naught. So that's the dynamics which you evolve in time. The other interesting that comes out of time-dependent type binding is that the density matrix becomes complex. Up to now, everything I've told you, I've been dealing only with real density matrices. Here, the density matrix is complex. And just like the force, or the energy, should we say, the total energy, I showed you the band energy is the trace of the Hamiltonian times the density matrix. If you take the trace of the Hamiltonian, or terms in the Hamiltonian times the imaginary part of the density matrix, the result is a bond current after multiplying by some fundamental constants. So we got the student to put the molecule into the state LUMO +2 and then to run these dynamics. And this shows the charge on the rightmost atom. Actually, the leftmost, this is the charge on the leftmost atom as it moves, as we drag the molecule down into the ground state. The dipole moment changes from pointing left to right to left, and charge smoothly transfers from one side of the molecule to the other, and that all looks very nice. And we noticed these little bumps and thought, well, I don't know what those are, probably just some little error, or we got him to go back and check, and he checked and there wasn't an error. And what we found was that these bumps were actually real. Quite interesting things were happening here. There were oscillations. If you blow the thing up in time, you see these very regular periodic oscillations in the charge. And then we looked at the charge in one of these atoms. So that's what we've plotted here. So the charge in one of these atoms is oscillating up and down. This is what these oscillations here are. So it takes a while for the thing to kick off, but after, 500 femtoseconds, all of a sudden you start to see charge oscillations here. The only thing that can mean is that you've got a bond current. You've got a current, and this is what we're plotting here, is the bond current. That's these oscillations here. So what's happening is that there are ring currents in this molecule as it decays into the ground state. So the currents are going like this, but then every 5 femtoseconds they change direction and go like this. So we've got a system which is oscillating. I think I'll end there. We have an explanation for that, but it's probably a good time to stop, isn't it? And people can ask questions and so on.